Ideal gas law. We've used the ideal gas law to solve for an unknown variable by comparing the final and initial states of a system. Now we can directly solve for the value of an unknown variable in a single given state. There we had final and initial states. To do so, identify the known values of variables and the unknown, rearrange the ideal gas law to solve for the unknown variable, convert the values of the known quantities to be in units compatible with an appropriate value of R. Substitute the values in and solve. When using the ideal gas law to directly solve for the value of an unknown variable, we need to use R, the gas constant. Its value depends on the units used for the variables. We have 8.314 joules per mole Kelvin. We have 0.08206 liters times atmospheres over mole Kelvin. And finally, 62.36 liters torr over mole Kelvin. What is the pressure of 2.4 moles of hydrogen gas at a temperature of 290 Kelvin and a volume of 4.6 liters? Here's our givens. And next we have to choose the form of R. In this case, we don't need to convert units and could use either of the second two forms of R shown here. It depends on what unit of pressure we want, atmospheres or torr. Let's use the second form and solve for pressure in atmospheres. We list our variables again along with the version of R that we would like to use for this problem. We then have the universal gas law. We want to solve for P, so we divide both sides by V, plug in all our numbers, and then the appropriate units cancel out, and we're left with 12 atmospheres. See, liters goes away there, moles goes away with moles inverse, and K goes away with K inverse. So we just have 12 atmospheres for our answer. What is the temperature in Kelvin of 32 grams of nitrogen gas that occupies 200 milliliters at a pressure of 450 millimeters of mercury? See this little point there? That actually has a meaning. That tells you that there are three significant figures there. Those zeros count. Here's our values. And next, choose the form of R to use, then convert the above units. We could use either of the second two, these two right here, since they include pressure. Let's use the second one and convert volume to liters, pressure to atmospheres, and mass to moles. So we start with our values, and then we have to make them consistent with our gas constant here. So our volume is 200 milliliters times 1 liter, which is 1,000 milliliters, and we get 0.200 liters. We convert millimeters of mercury to atmosphere by that conversion factor. 1 atmosphere is 760 millimeters of mercury. We get 0.592 atmospheres. And finally, we have a mass, which is 32 grams of N2 times 1 mole over the molar mass here, which is 28 grams, and we get 1.14 moles. And we use this value of the gas constant. Next, solve PV equals nRT for T and substitute in those values. Here are our givens appropriately converted so that they will match with our gas constant in the universal gas law. So PV is nRT. Solve for T by dividing both sides by nR. Substitute in our givens along with the units. Carry out the math, cancel out like units, and we get a temperature of 1.26 K. The number of moles of gas particles often changes following a chemical reaction. So here we have this equation here where we have 6 moles, right? 1 mole there, 5 here. And on the right side we have 3 plus 4, which is 7 moles. The change in moles will cause a proportional change in volume or pressure. If the pressure is held constant, then the volume would increase by 7 over 6. It's a direct relationship. If the volume is held constant, then the pressure would increase by 7 divided by 6, also a direct relationship. The below reaction occurs in a flexible container with an initial volume of 12 liters. What is the new volume after the reaction goes to completion? The temperature and pressure remain constant. We look at our reaction and we find we have 1 mole of gas initially, and then 1 plus 1, 2 moles finally. So here's our givens. We have our universal gas law, and we cancel like quantities and divide the two cases, the previous state and the final state. And we get V1 over V2 equals N1 over N2. We bring that up here, solve that for V2 by doing a little cross multiplying, substitute in our given and then what we found from the reaction equation, and we get the new volume is 24 liters. Or if you were in a hurry, since you doubled the amount of moles and you held temperature and pressure constant, the volume would also double. Data are often provided assuming that a gas is at standard temperature and pressure, or STP. STP is defined as a pressure of 1 atmosphere and a temperature of 273 Kelvin or 0 degrees Celsius. We learned earlier that 1 mole of any gas has a volume of 22.4 liters at STP. Now we can see why. PV is equal to nRT, and we're going to solve that for volume by dividing both sides by pressure. Let's put in all our numbers. We have 1 mole. Here's the gas constant in the right units. Here's our temperature at STP. And here's our pressure at STP. Carry out the math and look at that. You get 22.4 liters for 1 mole of gas at STP.